2.2 is on what's called the rank of a matrix. So looking at a matrix, we have already defined, but we'll consider three spaces related to an M by N matrix. We're going to look at what's called the column space, row space, and null space, which we have defined back in 1.6. We defined row space as the span of all the row vectors, column space, span of the column vectors. And so what we want to do is basically look at a basis for those different spaces. So what's going to be a basis? So you take the row vectors, you take the column vectors, and you do a span, and you automatically get a subspace of whatever dimension you're in. But it could, so if you have an M by N matrix, rows by columns, and you take the span of the rows, then the dimension of that set may or may not be M. It depends on if the rows are linearly independent, or the vectors defined in the rows are linearly independent. So that's what we'll be looking at, and kind of how to determine that, and some interesting properties. So write all this down. Let's see. So then the column, so row space is span of the row vectors, column space span of the column vectors. And then the span of the solution vectors of the homogeneous equation is called the null space. So we'll be looking at that as well. Let's underline that. Don't want to leave that out. The next definition is the dimension. So the dimension of the row or column space of A is called the rank of A. And theorem 2.1, and it doesn't matter what you say, row or column, shows that theorem 2.4 shows that the row rank equals the column rank. So it basically doesn't matter if it's M by N matrix, it actually has the same rank, meaning the dimensions of the space, the number of elements in the bases are the same. And we're just going to show that kind of by example. So you have an M by N matrix. So you have M rows and N columns, for example. Essentially what happens is it's either square and it's the same, and it can, or you're going to have stuff zero out. And that's essentially what's going to happen when you look at an M by N matrix. Okay, so to write that down, next, I'm going to this is a lot of writing, so I'm just going to copy. So next thing is this, and then the next one's example, and we'll get going on more examples. Okay, so next is this. This is what you do, the procedures to finding a basis for the matrix, for the row space and column space. So finding bases for spaces of matrix, so row, column, and null. So let A be an M by N matrix, and then you do row echelon form. So you have a matrix A, and then you're going to reduce it to a matrix of row echelon form. And we'll call that matrix, H. Then the row space of A, we use the non-zero rows of H. And I'll show you in the example below. And so basically, so you have to row reduce it all the way as far as you can. And then the row space for the basis. So this is defining a basis. What you use is a non-zero rows of H. So you'll have rows possibly zero out, and then you just use those. Okay. Column space of A, use the columns of A, not H, corresponding to the columns of H containing pivots. And so you go down and you say, well, take like the first one, and then maybe there's no change, you don't do anything. And the next one steps down again, and so you take that one. Right? So that's how you define the basis for the column space. And I'll show you that as well. Null space is solving that system. We've done that, and you just take those vectors. Okay, so you do the span of the solution vectors. Remember, you get those vectors t plus another vector s or something like that. So you just take these vectors, that you just span those. Okay, so this example basically have worked out, and we'll talk about it. So this example is, I'm not sure we can fit it all up there. We'll just put it here. Okay. So this is what you do. You take your, find a basis for the row space, column space, and null space. So you take your matrix A, right, and this is a 4 by 5 matrix, so it's your m by n. And then you row reduce it. So this is the row reduced echelon form. So you do row reduced echelon form as far as you can get, right? Do Gauss-Jordan elimination. And note right now that this row would not be there. I did that later. I didn't mean to do that. So this row right here, let's just do it in yellow, I guess. Right there, I put in there later so that I could calculate the null space. So it's really just these that you have. So now you look at the row space is pretty easy. You just take the non-zero rows. So this wasn't really here. So here, this row is zero, it's zeroed out. It's a linear combination of the other vectors. So these are the non-zero rows, 3 of them, 1, 2, 3. Okay, and then you take the, and notice I put a little note here. These vectors are in R5. So the number of elements in the space does not have to do with the Rn or M. So this has 1, 2, 3, 4, 5 elements in each vector. This one, the rows have 1, 2, 3, 4. So that doesn't change. It's the number of elements in the basis that has to be the same. So you take, so the next thing you do is for columns, you use the columns of A corresponding to the columns of H containing pivots. So the pivots are where you see the diagonal and you basically go across. So you got to take this one, which corresponds to this. So there you go. Now the next one down has a pivot. So you take this, which corresponds to this. So there you go. Now the next one over didn't change. Like you didn't step down to the diagonal. It's zeroed out. So you skip it and go to the next one. Now that one has a pivot right here. So you take this one, this column, corresponding to that row. And so there are your 3 linearly independent vectors we use for the column space. And then if you go across again, there isn't one, right? It's the same. It's zeroed out, so no pivot here. And you would know that it can't be, or you did something wrong, because there's already 3 elements in the row space. These must be equal. So just a little recap here. The dimension of the row or column space is called the rank of the matrix. So what's the rank of this matrix? Therefore, the rank of A would be what? Well, there's 3 elements. It has to be 3. Yes, the rank of A, it has to be 3. Okay. Now, let's continue. The next thing that has to do with rank is called the rank equation. So the rank equation is throwing in the concept now for the null space. So how many elements in the null space of the basis? Oh, I forgot to mention that. Sorry, I wasn't finished yet. Okay, so that I didn't show the details. So the null space is the span of the solution vectors from the null space. So I did not show all this steps. So you want to check this on your own. And so I wrote down x1, x2, x3, x4, x5. To do that, I had to write another row right here. So you have two free variables because both of these are zeroed out. And so x5 is arbitrary, x4 is arbitrary, and then you solve for those respective x3, x2, x1. Yeah. All right, so you'll end up with you'll end up with two free variables, this one and this one. And when you do that, you get two vectors for the solution space. So normally you'd say this times t plus this times s, right? So that, and then any of those are your solutions. Okay, so check this, see if that's what you get when you solve like we did back in chapter 1. Okay, so what we get for the rank equation, let's take a look at that. So this is called the rank equation. Okay, so, well, first let's talk about it. So first definition to define rank equation is the dimension of the null space of A is called the nullity. I'm trying to make this look a little better here. Okay, it's called the nullity of A. So the nullity is a dimension of the null space. So what's the dimension, what's the nullity of this matrix A? Well, you can see it'll be 2. Okay. Let's see. Okay, so this is the rank equation. Okay, so the rank equation is a somewhat simple idea. So for an M by N matrix, where row by column, right? A, the rank of A plus the nullity of A has to equal N, the number of rows in the column space. So, or the number of rows in the column space. So basically when you have stuff zero out, so this one had, up here had 1, 2, 3, 4, 5. Well, that's what you had, 1, 2, 3, 4, 5 rows all together. Okay. So you can basically want to check that. You want to be able to have a matrix, row reduce, and check the null space, column space, and make sure that number matches. So that'll be an example we do. Okay, so next theorem is 2.5. And this one kind of highlights everything. So this one says, let A be an M by N matrix with row echelon form H. So basically, they're giving you A, but then you're saying, okay, then row reduce it. Then 1, the nullity of A is equal to the number of free variables, basically the rows that zero out, but number of free variables in the solution space of AX equal to 0. So the homogeneous system. This also equals the number of pivot-free columns in H. 2, the rank of A, the rank of A is equal to the number of pivots in H. Or you just count, you do what you did above and kind of figure it out. But that's essentially what you're doing anyway. And then 3 is really just the rank equation. And then, so that's this guy. So the rank equation rank of A plus nullity of A is a number of columns in A. I'll even write that out. Number of columns. So, I mean, the number of columns in H will not change. I mean, you could get things to zero out, but it's not going to change the number of them. Okay. One of the results of all this gives us theorem 2.6. So what if you have an invertible matrix, basically? What happens? So theorem 2.6 says an n by n, so a square matrix, A is invertible if and only if the rank is what? So matrix A is invertible if and only if, well, what would the rank have to be for it to have invertibility? Well, think about it here. The rank of A is the number of columns of A. I mean the number of pivots. And so what does the nullity have to be if you have an invertible matrix? Right? You can't have stuff zero out, right? Invertible matrix, one of the results was we have a unique solution. Well, you can't have an entire row to zero out and have a free variable, right? So the rank has to equal what? Not very talkative today. Has to be n. So think about it. Does that make sense? Like, why would that make sense? Okay, it's putting all this stuff together. That has to be true because there can't be any free variables for the matrix to be invertible. So the rank has to match the number of columns. So picture it just being row reduced to the identity matrix. You're going to have a pivot in every column. So, okay, so that has to be true. Okay. Next few examples we'll look at. We'll check some cases out, find the rank of A, basis, row space, column space, null space, and confirm the rank equation. So we'll do at least one or two more, work it out more carefully. Well, to actually do it. One very similar to this, which we kind of did it already here. This shows pretty much everything you would need to continue. So find the rank of A, we pretty much did that. Basis for the row space, we did that. Basis for the column space, did that. Basis for the null space, did that, although it didn't show it. We'll show it next time. And confirm the rank equation. So let's confirm the rank equation for this guy up here. The rank equation, so what's the number, what's in? This was 1, 2, 3, 4 by 5. So in is 5. So the rank equation would have to be 5 is equal to the 3 in the rank plus the 2 in the null space. Okay, so that's true. So that's one of the questions that you might be asked for sure. Okay, we'll do a few examples of that, or at least one. And then we'll go on to 2.3.